Welcome to our session on data balancing in artificial intelligence. Today we are discussing a vital concept in the world of AI auditing. We will explore why simply having enormous amounts of information does not guarantee a smart or fair artificial intelligence system. We will look closely at how uneven datasets cause AI models to make critical mistakes, and we will break down the specific techniques organizations use to correct these issues. Understanding data balancing is highly practical for your everyday career. Whenever your company is evaluating a new automated system, whether it is software that screens vendor applications or a tool that reviews legal contracts, you need to know how to ask the right questions about the training data. Knowing how to spot unbalanced data allows you to protect your organization from deploying biased tools that could lead to unfair practices, regulatory fines, or severe reputational damage. Let us start by looking at the reality of how information is gathered today. Modern digital environments generate an overwhelming volume of data every single day. Think about the massive amounts of text messages, digital images, streaming videos, and audio files created by daily communications. Consider the endless stream of data from social media interactions, or the sensor data pumped out by machines and factory systems. It seems like we have an infinite supply of information to teach our AI systems. However, the reality is that not all of this generated data is actually captured, collected, and made universally available to the systems that train AI models. Because of how data is collected, uneven distributions occur naturally. When an organization trains an AI model using a dataset that is highly skewed, meaning it heavily favors one type of information over another, the model will inevitably produce a higher rate of inaccurate outcomes. This brings us to a very common challenge in AI development known as data imbalance. Data imbalance happens when the information used to train the system lacks sufficient samples of a specific, smaller category of data. In the industry, this underrepresented category is known as a minority class. The root cause of failure here is simply a lack of sufficient and diverse data during the learning phase. Let us use a simple analogy. Imagine you are training a quality control robot for a fruit packing plant. You want it to sort apples and pears. If you feed the robot 10,000 pictures of apples, but only 5 pictures of pears, the pears represent our minority class. The robot will become an absolute expert at identifying apples, but it will likely produce highly inaccurate results when it sees a pear. It might categorize the pear as a strangely shaped apple or simply reject it as an error. The AI becomes biased toward the information it sees most often. When developers realize their training data is imbalanced, they face another significant risk. Organizations sometimes panic and overcompensate. They try to boost the presence of the minority class data so much that it no longer reflects the real world. Going back to our fruit plan, if the developers artificially manipulate the data so the robot thinks the facility processes 50% apples and 50% pears, the robot will start mistakenly identifying bumpy apples as pears. Overcompensating destroys the real-world distribution and creates an entirely new set of biased outcomes. To prevent these issues, organizations must address data balancing very early in the model development process. The first actionable mitigation step is data profiling. Profiling means thoroughly evaluating and understanding the distribution of your data during the initial collection and pre-processing stages. Pre-processing is just a technical term for cleaning and organizing the data before the AI ever sees it. You cannot balance a scale if you do not weigh the items first, and profiling is how developers weigh their data. Once the distribution is understood, developers use 3 main techniques to improve model performance. The first is oversampling. Oversampling involves carefully increasing the number of examples in the minority class to make it more prominent. The second technique is undersampling. Undersampling takes the opposite approach by intentionally removing examples from the overwhelming majority class until things are more balanced. The third technique is applying cost-sensitive algorithms. A cost-sensitive algorithm simply means programming the AI to face a much heavier penalty if it makes a mistake regarding the minority class. Think of it like a driving test. You might lose 1 point for parking slightly crooked, but you will instantly fail the test for running a red light. Cost-sensitive algorithms force the AI model to pay very close attention to the rare minority class data by making mistakes incredibly costly during the training phase. Let us recap the main takeaways from this session. We learned that despite generating massive amounts of data, the information collected for AI training is often skewed, leading to data imbalance. This lack of diverse data creates a minority class, which causes the AI to produce biased and inaccurate results. We explored the danger of overcompensating and losing sight of real-world distributions. Finally, we discussed critical mitigation steps, including early data profiling, oversampling, undersampling, and applying cost-sensitive algorithms to improve performance. All the important topics and concepts from this session are covered in the multiple choice questions on RooCloud.com. You should ideally solve the chapter-wise questions to reinforce your learning before moving to the next session. Thank you for joining me, and best of luck with your continuing studies.